Right. Good evening, guys. First of all, before starting, is my audio clear? Is my audio and video clear for y'all? Drop me a message in the chat box. Is it clear for y'all? Right, okay, right. So today what are we gonna do? We are gonna start industrial chemistry, right? So before going into the unit, let me tell me something about the paper, right? So industrial chemistry unit, if you take in the paper, you will have 5 MCQs, right? You will have 5 MCQs from industrial chemistry. Apart from that, you will have a complete essay on industrial chemistry, right? Mostly the 10th question, 10th essay, right? 10th essay is completely on industrial chemistry, right? So you can see one complete essay and you will be getting around 5 average 5 MCQs you will be getting for the paper on industrial chemistry unit, right? So you will understand the importance of this unit, right? Because without this unit you will be losing nearly 12 marks, right? 12.5 marks. So 5 MCQs you will have 1 marks and 5 marks for the MCQs, and one complete essay you will have out of 100 you will have 7.5 marks, right? So around 13 marks out of 100 you will be having for industrial chemistry, right? That's how the industrial chemistry is tested in the paper. Now, industrial chemistry, what do you have inside industrial chemistry unit, right? What do you have? So you will have mainly 9 industries. You are having 9 industries inside this unit. Apart from that, you are having environmental chemistry, which is we are mainly talking about global warming, acid rain, about those things, right? Environmental chemistry. And you have plant oils, like plant oils, right? Regarding plant oils, you'll be having like steam distillation, fractional distillation, those are there. And you have polymers, right? Water parameters, like that you have some few, right? This is the content of the industrial chemistry unit, right? So today, right, if you are asking me whether there is a link between industrial chemistry and any other previous units, I will probably say no, right? Because few knowledge of equilibrium is needed, but that will not create a major impact for this unit, right? So this is like a separate unit. If you have not followed equilibrium, or if you don't know kinetics, that doesn't matter. This is a separate unit, so you can study from this unit, right? So out of 100 you will have 12.5 marks if you study this unit thoroughly and perfectly, right? Then without getting late, let's get into the unit chapter, right? Inside industrial chemistry we have the first industry, that is magnesium extraction, right? Magnesium extraction, this is the first industry that we are going to discuss today, right? So this is a very short section, magnesium extraction. So we have another name for this process, right? We call this as the Dow process, right? Another name is Dow process. Wait, let me check the video. Right, not visible, right? Magnesium extraction. We have another name, Dow process, right? Before going into the magnesium extraction, why do we need magnesium? Why do we need magnesium? If there is a purpose only, we need to produce magnesium, right? So why do we need magnesium? Right, children, guys, magnesium, if you take, it's a very special metal, right? It's a very strong metal, right? Magnesium is a strong metal. Also, it is a very light metal. Very light means it's not heavy, right? It's not heavy. So magnesium is a strong metal as well as a very light metal. It's not heavy. So therefore, this magnesium is used in aircrafts, right? Aircraft means what? Aeroplanes, right? In manufacturing aeroplanes, they use this magnesium. Also in vehicles, this magnesium is used, right? So as magnesium is a strong metal as well as a very light metal, this is used in aircrafts and vehicles. So that is the purpose of producing, that is the use of magnesium for us, right? So therefore we are extracting magnesium, right? Now why do we need to extract magnesium? The reason is we can't find magnesium naturally. Naturally magnesium is not available, right? So naturally what can we find? We can't find magnesium, but we can find magnesium 2 plus. Naturally we can find magnesium 2 plus, right? Naturally we can find magnesium 2 plus, right? Now where can we find this magnesium 2 plus? So magnesium 2 plus can be found in two places, right? One is from the earth crust. You can find magnesium in earth crust, right? And second thing, you can find all magnesium 2 plus also in the sea water, right? So let me repeat again. Why do we extract magnesium? Because we can't get magnesium naturally, right? We can't get magnesium itself, right? Magnesium metal we can't get it, but we can get magnesium 2 plus, right? From the nature we can get magnesium 2 plus. Now where can we find this magnesium 2 plus? We can find this magnesium 2 plus inside the earth's crust and also in the sea water. These are the two places where you can find magnesium 2 plus naturally, right? So what are we going to do is we are going to take this magnesium 2 plus fellow, and we are going to produce magnesium from it, right? Right. Now you tell me, children, from where, if you take magnesium 2 plus, you can get it from earth crust and sea water, right? So now getting magnesium 2 plus from earth crust is easy, or getting magnesium 2 plus from sea water is easy. Which one is easier, right? Tell me. Getting magnesium 2 plus from earth crust is easy, or getting magnesium 2 plus sea water is easy? Which one is easy, right? Obviously sea water is easy, right? Why? Earth crust, what it's a, if you take earth crust, you have to go inside the earth, right? It's near to the core. Just outside the core is the crust, right? So you have to dig inside the earth, right? So for that you will need high machineries. So it's a very highly expensive process, right? It's a very high expensive process. So getting magnesium 2 plus from the earth crust is very expensive. But sea water, what about sea water? If you go to the beach side, you can get magnesium 2 plus from the sea water, right? So this is very easily accessible, right? So first point remember is magnesium 2 plus can be obtained from earth crust as well as from sea water, but obtaining magnesium 2 plus from sea water is more profitable, right? So therefore what we are doing is we are taking the sea water, right? Now we are taking the sea water, right? So this is the sea water. What is this? Sea water. Let's assume that you are taking a sample of seawater, right? This is a sample of seawater. Now when you analyze this seawater, what will be the ions that will be present inside this? So definitely seawater will have ions inside it, right? So what are the ions that will be present inside the seawater? Any ideas? Any ideas what will be the ions present in the seawater? Right, okay, let me tell. So if you take a seawater, the ion that will be most available in this seawater will be sodium plus, right? Sodium plus will be the most available ion inside this seawater, right? That is the most available, the ion that is present in higher amount. And the ion that will be present in second higher amount, right? That means first one is sodium plus, the second highest one is magnesium 2 plus, right? And apart from that you will have other ions also, right? But our motive is to get magnesium 2 plus, right? So let me repeat again. If you take a sample of seawater, you will have ions inside it, right? So when you consider the ions, the ion that will be most available in the seawater is sodium plus, and the second most available ion is magnesium 2 plus. Now we need magnesium 2 plus to produce magnesium, right? So what should we do? First we should remove the sodium plus from the seawater, right? First we must remove the sodium plus from the seawater, then you can take the remaining solution and you can go with the process, because that remaining solution will have magnesium 2 plus, right? Now what are we going to do is we are going to find a way to remove the sodium plus ion. So what are we going to do is, you know, salt production, right? In salt production what we do, we are taking the seawater and we will be removing the sodium plus and we will be producing sodium chloride, right? So the solution, right now after, right, let me tell again. So what are we in salt production, what is done? Seawater is taken, sodium plus is precipitated as sodium chloride, crystallized, right? Crystallized as sodium chloride, and there is a process, right? There is a certain process, but what we need is, we need the remaining solution after removing sodium plus. In salt production what they do, they take the seawater, right? They take the seawater and they remove the sodium plus ions from it. Remove sodium plus ions from it, right? And the remaining solution, there is no use for them. For whom? For the people who are producing salt. For them the remaining solution is of no use, right? For them there is no use from the remaining solution, right? But for the people who are producing magnesium, there is a use out of this remaining solution, right? As I said before, seawater, what you will be having? Magnesium 2 plus, sodium plus and other ions, right? Now in the salt production, sodium plus is removed, right? Sodium plus is removed, and what will be the ions present in the remaining solution? Seawater, yeah, will be having sodium plus and magnesium 2 plus, and after removing sodium plus ions in the salt production, the remaining solution will have, mainly there will be magnesium 2 plus, right? Mainly there will be magnesium 2 plus, also there will be other ions also, right? But sodium plus will not be present, right? So we give a special name for this remaining solution. What is it? This remaining solution is known as the Bittern solution, right? This remaining solution is the Bittern solution, right? Let me repeat again once again. Let me repeat it. Right, magnesium 2 plus you can get it from the earth crust and seawater. Now obtaining magnesium 2 plus from the earth crust is very expensive. Therefore we are going with the seawater, right? When you take the seawater, you will have mainly two ions. Apart from that there will be many ions also, mainly two ions. The ion that is most available is sodium plus, and the second most available ion is magnesium 2 plus. Now you need magnesium 2 plus to extract magnesium. Therefore what you should do is, first you must remove sodium plus from the seawater. For that what we are going for a salt producing factory, right? You can go for a salt producing factory, and what can we do is, after they will also use the seawater. Salt producing industries also, they will use the seawater and they will remove sodium plus ions from it. And what we can do is, we can take the remaining solution after removing sodium plus to produce magnesium extraction, right? So that remaining solution is given the name bittern, right? So this is from this bittern solution we can produce magnesium 2 plus, right? Okay, so no need to write. Okay, so I'll be reading the resource book at the end also, so I will tell to highlight the important points. That is enough for your knowledge. Okay, all right. So this is the introduction. Now you have got the bittern solution, right? Now we have some few steps in the magnesium extraction process, right? Step 1, what are we doing is, right, now you have this bittern solution, right? Assume that you are pouring into a tank, right? You are pouring this fellow into a tank, bittern solution, right? Okay, now you are having magnesium 2 plus inside it. Apart from that, you have other ions also, right? Now we have some few steps in magnesium extraction. The first step is the thermal decomposition of calcium carbonate, right? Right, let me explain it again. Right, calcium carbonate, what we are doing is we are taking calcium carbonate, right, or else we can call it limestone. So what we'll be doing here is we'll be heating calcium carbonate, right? We'll be heating calcium carbonate. Why is it heated? You will understand with the flow, right? So what first step what we'll be doing is we'll be heating calcium carbonate, right? So when you heat calcium carbonate, what will you get? You will get calcium oxide and carbon dioxide, right? First step what we'll be doing in magnesium extraction is heating calcium carbonate, right? So next what you will do is, so you will have some you will be having bittern solution in your tank, right? Let's assume you are putting a tank and you are filling it with bittern solution, right? So what you will be doing here is you will be adding this formed calcium oxide into the bittern solution, right? What you will be doing in the second step is you will be adding calcium oxide into this bittern solution, right? What happens when you add calcium oxide into this bittern solution, right? Before going for that, what are the species present inside this bittern solution? What are present? First is magnesium 2 plus is present, right? Obviously magnesium 2 plus is present, right? Other ions also present inside this, but we are considering magnesium 2 plus because that is the one that is needed, right? So mainly magnesium 2 plus is present. Apart from that, what you have water, right? You have water because this is a solution, right? Bittern solution, right? Bittern solution, so definitely there will be water. Only ions won't be present, right? So there will be definitely water, right? Now what happens is the moment you add calcium oxide to the bittern solution, calcium oxide starts to react with water. What happens? Calcium oxide starts to react with water. So let me write it. Calcium oxide reacts with water, and what does it form? Calcium hydroxide, right? It forms calcium hydroxide, right? Next what happens is this calcium hydroxide, wait, let me get some space and let me draw it here. This is the bittern solution and you added calcium oxide to this, right? You added calcium oxide to this, and the species present mainly in the solution is magnesium 2 plus and water. Now what happens is the moment you add calcium oxide to this bittern solution, the water molecules in the bittern solution reacts with calcium oxide and forms calcium hydroxide, right? This is what happens in the second step. Then what happens is this calcium hydroxide dissolves partially in the bittern solution. What does it happen? It dissolves partially, right? Now how does it dissolve then? Calcium hydroxide dissolves to calcium 2 plus and 2OH minus, right? It dissolves partially in the solution. Now what happens is this formed OH minus hydroxide ions will combine with the magnesium 2 plus in the bittern solution and form magnesium hydroxide, right? So third step, what happens is this OH minus, right, will combine with the magnesium 2 plus, right? It will combine with the magnesium 2 plus and it will form a white precipitate, magnesium hydroxide, right? Magnesium hydroxide will be formed, right? This is a precipitate, right? So this is the step happening in the this is the step that is happening in the tank, right? So second step is basically inside the tank. What is happening? First of all, you are burning calcium carbonate and you will be getting calcium oxide. Next, you will be adding calcium oxide into this bittern solution. When you add calcium oxide into the bittern solution, calcium oxide will react with the water inside the bittern solution and form calcium hydroxide. This calcium hydroxide will dissolve partially, giving calcium 2 plus ions and hydroxide ions, right? And next, these hydroxide ions will start to combine with magnesium 2 plus and will form magnesium hydroxide, which is a precipitate. Now what happens? This magnesium hydroxide will float, right? It will be present as a precipitate in the tank. So this is the tank, bittern solution tank, and you will be able to see magnesium hydroxide like this. So there will be a solid form, right? So this is the magnesium hydroxide. Now in the third step, what are we doing is we will be removing this magnesium hydroxide by filtering, right? What do we do? We will be removing magnesium hydroxide by filtering, right? By filtering, like you all know, right? Filtering, you all take a filter paper, right? If you do it in a small scale, you will need a filter paper and you will be filtering, right? But this is industry, right? So there are methods to filter. However, you will be filtering magnesium hydroxide and you will be taking out in the third step, right? So the 4 magnesium hydroxide is taken out, right? And what we will do is we will be adding conc HCl to this, right? We will be adding conc HCl. Conc HCl to this magnesium hydroxide, and what will you get? You will be getting magnesium chloride, right? You will be getting magnesium chloride. Apart from that, water will also be formed, right? Water will also be formed. What we are doing, we are taking the precipitate formed in the second step by filtering, and we will be adding conc HCl to it, right? So when you add conc HCl, you will be getting magnesium chloride and water. So this is the third step, right? So yeah, okay. Now fourth step, what do we do in the fourth step, right? So I don't have space here, let me erase this, right? In the fourth step, what do we do is we'll be taking this magnesium chloride, right? In the fourth step, we'll be taking the magnesium chloride, right? Now when you take this, consider this magnesium chloride, what is present? Magnesium chloride aqueous, right? Magnesium chloride aqueous means you will be having magnesium, chlorine and water. You'll be having water, right? Because aqueous, right? So definitely we'll be having water. So what we'll be doing is we'll be heating this to evaporate water. We will be heating this, right? We will be heating. So we will be heating magnesium chloride and evaporate water. Then you will get magnesium chloride dot 6H2O, right? So what does this 6H2O mean? I will explain it in a while, okay? In a while I will explain this, right? Now what we'll be doing is we'll be further heating. We'll be keep on heating, and then what happens is magnesium chloride dot 6H2O will convert to magnesium chloride dot 4H2O, right? And further we'll be heating, and this magnesium chloride dot 4H2O will be converting to magnesium chloride dot 2H2O, right? So what we'll be doing, we'll be taking the magnesium chloride formed in the third step and we will start to heat it. Why do we heat? To remove the water inside this, right? So when you heat it, what will happen? It will be forming magnesium chloride dot 6H2O solid, right? And we will be heating it further, and we'll be heating it further, right? So what does this dot H2O means really? Right, let's take you are having a solid, right? This is a solid. Let's assume that this is the magnesium chloride, right? So this will absorb some water, right? This will absorb some water. It will absorb some water molecules inside it. And this absorbed water molecule is shown as dot H2O, right? So magnesium chloride solid and the absorbed water molecules, the water molecules surrounding it, right? So what we are doing is we are keeping on heating. We are keeping on heating to remove water. Right, finally if you heat you will get this one. After this you will be not able to remove this water, it's very difficult. And next what we'll be doing is we will be melting this. This is a solid, right? This is a solid, right? So what we'll be doing is we will be melting this. So fusion will take place. Wait, right, fusion will take place. Magnesium chloride dot 2H2O solid will be fused or melted, right? If melted, what will happen? If it is heating to the melting temperature, what will happen? This H2O also will evaporate, right? So then finally what will you have? You will have magnesium chloride liquid, complete liquid you will have, right? So we are heating and finally we are fusing it also, right? Fusing it and we are taking to magnesium chloride liquid, right? So next what we'll be doing is we will be electrolyzing this. We will be passing this magnesium chloride to through an electrolysis process. We'll be passing this, okay? So what we will be doing is so there is a setup industrially, there is a setup, right? So that is not needed for y'all, just the idea is needed, okay? So you'll be having an anode and the cathode, right? I hope y'all can see it, right? It's visible, right? You'll be having a beaker. Inside this you'll be having two electrodes, right? What are these? These are electrodes. And what you'll be doing is you will be filling this with magnesium chloride, right? This is magnesium chloride liquid, okay? Magnesium chloride liquid, right? What we do is we basically transfer this magnesium chloride into this, right? That is what is happening. And then you will connect these electrodes to positive and negative, like that we do. So that is an industrial setup, right? So if you have studied electrochemistry, right? So the electrode, so I'll tell the theory also. The electrode connected to the positive terminal of the cell is known as the anode, right? The electrode connected to the positive terminal of the cell is known as the anode. So this is the anode. Right? The electrode connected to the negative terminal of the cell is the cathode. So this is the cathode, right? Right. Right. And reduction. Now you have, if you have studied chemical calculation, you know there is reduction and oxidation, right? So in the cathode what happens is reduction, right? So that is electrochemistry theory, but the theory is this, right? Always reduction takes place in the cathode. That is the theory you need to know. Always reduction takes place in the cathode, right? Then what takes place in the anode? Anode oxidation takes place in the anode, right? Oxidation takes place in the anode and reduction takes place in the cathode, right? Now tell me the cathodic reaction and the anodic reaction. So cathodic reaction, if you take, right, cathodic reaction, reduction must take place, right? Now what are the ions present in this inside this setup? You are having only magnesium chloride, that is also liquid, so the ions present will be magnesium 2 plus and Cl minus. Those are the two ions present inside, right? You'll be having magnesium 2 plus and Cl minus, because magnesium chloride, if you ionize it, you will get magnesium 2 plus and Cl minus. Then one of the species is gonna oxidize and one of the species is gonna reduce, right? So which one can oxidize, right? Which one can reduce? Can Cl minus reduce further? Chloride, can it reduce further? No, right? It can't reduce. So only possible species that can reduce is magnesium 2 plus. And also I said reduction takes place in the cathode. So the reduction reaction is the cathodic reaction, right? So the species that gonna reduce is magnesium 2 plus. So magnesium 2 plus is gonna reduce to what? Magnesium 2 plus is gonna reduce to magnesium, right? And the magnesium formed here is liquid. I'll tell why, right? I'll tell why in a while, okay? So the cathodic reaction is magnesium 2 plus receiving 2 electrons and going to magnesium liquid. This is a reduction reaction, and out of these two species only magnesium 2 plus can reduce, right? So this is a reduction reaction, and reduction always takes place in the cathode, therefore this is the cathodic reaction. And what about the anodic reaction then? Anodic reaction, then oxidation is gonna take place, right? Oxidation is gonna take place, right? So who is gonna oxidize? Will magnesium 2 plus oxidize further? No. So chloride is gonna oxidize, right? So chloride is gonna oxidize to Cl2 gas, right? Not Cl2 gas, right? Plus 2 electron, right? This is what is gonna happen here, right? And in the anode side oxidation takes place. That is the electrochemistry theory, right? Right. So species that is going to oxidize is chloride, Cl minus ions, right? So Cl minus will be oxidizing to chlorine by releasing 2 electrons, and finally you will get the magnesium from this electrolysis setup. And what you will do is you will cool this magnesium, and this liquid magnesium can be converted to solid. By that you can get the magnesium, right? So that is the whole whole process, right? Let me go a quick overview about this, okay? Let me go a quick recap, okay? First of all, why do we need magnesium? Magnesium is a very light metal, and also it is a very strong metal. Therefore it is used in aircrafts and vehicles. So magnesium is very important to produce alloys with this kind of properties. I'll tell where to highlight, okay? You all these are available in the resource book, no need to write. I will read the resource book and I'll tell where to highlight, okay? And that is the use of magnesium, right? Now there is a use of magnesium. Next one, why do we extract magnesium, right? Because naturally you won't be able to get magnesium, right? But you will be able to get magnesium 2 plus naturally. So where can you get this magnesium 2 plus from? You can get it either from the earth crust or from the seawater, right? But obtaining magnesium 2 plus from the earth crust is very expensive. Therefore you will need to get it from the seawater, right? Because obtaining magnesium 2 plus from the seawater is more profitable, right? Now when you take seawater, what are the ions present inside it? The ion that is mostly available in the seawater is sodium plus, and the second most available ion in the seawater is magnesium 2 plus, right? So in order to obtain magnesium 2 plus, first you must remove sodium plus from the seawater, right? So I have erased that part, right, due to lack of space. If you all want, you can go that and you can take a screenshot, okay? because this is a recording, right? So you can go right. In the seawater you will be having sodium plus and magnesium 2 plus. So in order to obtain magnesium 2 plus, first you must remove sodium plus, right? So what are we doing? So we'll be going to a salt producing factory, and we'll try to take the remaining solution after extracting sodium plus. So in the salt factory, what they do, in the salt industry, what they do basically, they'll be taking the seawater and they will start evaporating it, right? So finally sodium chloride will be crystalling out. So in the seawater, in the salt producing industries, they will remove the sodium plus, right? And we in the magnesium production, we need the remaining solution after removing the sodium plus, right? The seawater, after removing sodium plus, the solution, some solution will be remained, right? So that solution is given a special name called the bittern solution, and that bittern solution is used to extract magnesium, right? So then then after that we are having some processes in order to produce magnesium. The first process is burning calcium carbonate, right? What do? Is we decompose calcium carbonate. So calcium carbonate decomposes to produce calcium oxide and carbon dioxide. And next what we do, we'll be adding this calcium oxide into the bittern solution, right? So bittern solution, if you take, you'll be having water inside it, and also magnesium 2 plus will be present. So the moment you add calcium oxide into the bittern solution, calcium oxide will react with the water present in the bittern solution and form calcium hydroxide, right? And this calcium hydroxide will dissolve partially in the bittern solution to produce calcium 2 plus and 2 hydroxide ions, right? And the formed hydroxide ions will react with the magnesium 2 plus present in the bittern solution, and it will precipitate magnesium hydroxide, right? So the second step, all the process, the steps in the second scenario also is related to the bittern solution present in the tank, right? So these steps are happening in the tank, okay? These steps are present in the tank, right? And the third step, what happens is this formed magnesium hydroxide is filtered and taken out separately, right? It's taken out separately, and we add conc HCl to it. So after adding conc HCl, you will have magnesium chloride aqueous and water formed, right? And next what we do is we'll be heating this magnesium chloride aqueous in order to remove water. So if you heat it, you'll have magnesium chloride dot 6H2O solid, right? And when you keep on heating it, finally you will get magnesium chloride dot 2H2O. Then what we do is we'll be fusing it, or we'll be melting this, okay? So when you melt, magnesium chloride dot 2H2O solid will be converting to a magnesium chloride. When you heat this, right, when you fuse this, the water present in the solid will be evaporating, right? And finally what happens is you will be transferring this magnesium chloride into the chamber where the electrolysis happens, right? So this is the simple setup. So industry, you're having a little bit different setup, but this is the basic idea, right? So what you do is you'll be transferring magnesium chloride, and you'll be having two electrodes connected to a cell, right? So the electrode connected to the positive terminal, the electrode connected to the positive terminal of the cell is given the name anode, and the electrode connected to the negative terminal of the cell is given the name cathode, right? So in the cathode always reduction takes place, and in the anode always oxidation takes place, right? Now if you take the solution, you are having only magnesium chloride, right? It's a liquid. So if you consider the ions, you will be having magnesium 2 plus and Cl minus ions. Then one of these ions is gonna oxidize, and one of the ion is gonna reduce. So if you consider the cathodic reaction, reduction must takes place, and the ion that can reduce out of these two is magnesium 2 plus, right? So magnesium 2 plus will be reducing by taking 2 electrons to magnesium liquid, and at the anode oxidation takes place, and the species that can oxidize is only Cl minus out of these two, right? So Cl minus will be oxidizing to Cl2 and by releasing 2 electrons, right? So finally you will be having magnesium liquid near the cathode, and by cooling this magnesium liquid you can get the magnesium solid, right? So then you will be having magnesium, right? This is the process, right? I hope you got the idea. Now I have to add some extra points, right? Extra points in the sense, right? I have to add some extra points. First extra point I have to add is in the step 1. So what are we doing? We are heating calcium carbonate, right? We are heating calcium carbonate. If you don't have calcium carbonate, you can use another alternative. Instead of calcium carbonate, you can use another alternative, that is dolomite, right? You can use dolomite. Right, you can use dolomite instead of calcium carbonate, right? So there is a reaction for it. I'll explain it separately, right? So you can use either calcium carbonate in this step 1, or you can use dolomite, right? Or you can use dolomite. Dolomite is calcium carbonate dot magnesium carbonate, right? So instead of calcium carbonate, you also can use dolomite also in the step 1, right? And the second thing I wanted to add here is, so in the resource book they have given this as a reversible reaction, right? So write it as a reversible reaction, okay? So the second stick I wanted to add is, if you burn calcium carbonate, will all the calcium carbonate convert to calcium oxide? No, all the calcium carbonate won't convert to calcium oxide, because this is a reversible reaction. So at the end of the heating process, you will be having both calcium oxide and calcium carbonate, right? Both will be present, because this is an equilibrium reaction, right? So both will be present, and this is an advantage in this, disadvantage in the step 1, right? What is the disadvantage in the step 1? Precipitation of calcium carbonate along with calcium oxide, right? Because at the end of the decomposition, you will be having both calcium carbonate and calcium oxide. So that is a disadvantage, right? So that is another extra point that you need to remember, right? Apart from that, here also in the step 2 also you will be having a disadvantage. What is the disadvantage? Any ideas? Look at the reaction and tell me. Right here. So calcium hydroxide will be producing OH minus, and these OH minus will convert to magnesium hydroxide, right? So if you add some excess, there is a like how can I tell you, right? If you add excess calcium hydroxide, you will be having excess OH minus, right? So if you're having excess OH minus, then magnesium 2 plus will finish it off. At one point it will finish, and there will be magnesium hydroxide as well as calcium hydroxide will be present. So you have to be very careful when adding calcium hydroxide to the solution, right? When you're adding calcium oxide to the solution, because if more calcium hydroxide is present than magnesium 2 plus, right, then you will be precipitating magnesium hydroxide and calcium hydroxide, right? So what happens? From calcium hydroxide only you will be getting OH minus ions, right? So if the OH minus ions formed is very high, then magnesium 2 plus will become a limiting reactant, right? So then all the magnesium 2 plus will be precipitating as magnesium hydroxide. Also there will be some calcium hydroxide also remaining, so that is a disadvantage, right? So I said this for an extra knowledge. End of the day, what you have to remember is, the disadvantage in the second process is precipitation of calcium hydroxide along with magnesium hydroxide, right? So that is a disadvantage in the second step. First step, what is the disadvantage? Presence of calcium carbonate along with calcium oxide, right? So that is a disadvantage in the second step. Also there is a disadvantage in the first step, I said, okay? And next thing I have to mention here is, right, now other things. So you can see that chlorine is producing in the electrolysis process, right? So chlorine is, there is no use, right? If you just leave, it's a waste for us, right? What you can do is, you can use this chlorine, right? You can use this chlorine and you can produce HCl, right? You can produce this HCl, right? Using this chlorine you can produce HCl, right? Otherwise what you have to do, you have to buy conc HCl from outside, which is another expense for y'all, right? Because now y'all can think, sir, poddaine on HCl, so it's not that much expensive, like that you can think, right? But this is a very industrial process. This takes place in very large amounts, right? So what the advantage you can get from this anodic reaction is, you can reproduce HCl from chlorine, If you want, I can write the reaction also. What you can do is, this is not given in the resource book, okay? So you can react the formed chlorine gas with water, right? You can react it with water and you can form HCl. Apart from that, you can form oxygen also. This is not given in the resource book, okay? This is just for extra knowledge, but you have to remember that this chlorine gas is used to reproduce the conc HCl, right? That is an advantage of this chlorine gas. Let me balance it. 2 chlorine, 2 water, 4 HCl, right? 4 HCl, right? So there is an advantage of this chlorine gas. What is that advantage? We will be reproducing the conc HCl, right? So next thing is this magnesium produced, right? You have to remember the purity of it. The purity of magnesium is 99.8%, right? 99.8%. That is the purity of magnesium liquid, right? Apart from that, what is the temperature of this setup, right? We are heating this, right? We are fusing it, right? So normally the temperature is between 700 degrees Celsius to 800 degrees Celsius, right? So temperature is 700 degrees Celsius to 800 degrees Celsius. So I'm having lack of space to 800 degrees Celsius, okay? This is the temperature, right? 700 to 800 degrees Celsius is the temperature of this setup. So also you have to remember that, right? Okay, so that's it, right? So dolomite scenario, let me explain it. So what happens if you use dolomite? I'll explain it, right? There is also another one extra point. Now you are doing this industry, right? You are producing magnesium, everything is happening, but you should consider the environment also. Is there any effects to the environment? You should consider that. Now you can see, while burning calcium carbonate, CO2 is released to the environment, right? CO2 is released to the environment, which is a effect to the environment. Why it impacts environment? What is the negative impact of this CO2? If you will study further in the syllabus, or you might also have knowledge on environment, that is global warming, right? So the major gas that contributes to global warming is CO2, right? CO2 is the major gas that will be converting to CO2 will be the main gas that will be the forming the global warming, right? So here CO2 is produced in this extraction. First is, while decomposing calcium carbonate, CO2 is removed to the atmosphere. Apart from that, you can see you are heating this, right? So the temperature is 100 to 800 degrees Celsius. Can you just get this temperature? නිකන් අර උඩ බලාගෙන හිටියොත් මේ temperature ගන්න පුළුවන්ද? No, right? You can't get this temperature. These are very high temperatures. So what you need to do, you have to combust petroleum products, right? So mainly petrol is used, might be, right? So you have to combust. These are very high temperature, right? So you have to combust, right? So while combusting the petroleum products, so mainly you'll be combusting petroleum products to heat the setup. So while combusting these petroleum products also, CO2 will be released, right? So CO2 is released to the atmosphere by two ways. First is by burning calcium carbonate, CO2 is removed, okay? And the second one is by the combustion of petroleum products to reach this high temperature also, CO2 is released to the atmosphere. So by these two methods, CO2 is released to the atmosphere, which can cause global warming, right? So that is the environmental impact, right, of this magnesium extraction process, right? So that's it, all the points I explained. I have to explain what happens if dolomite is used, right? So nothing, right? Nothing seriously happens. I'll erase this part, okay? So then we'll be reading the resource book and then we'll be finishing it off, okay? Right. So if calcium carbonate is used, you will have calcium oxide and CO2. If dolomite is used, what happens? If dolomite is used, that is calcium carbonate dot magnesium carbonate. If you use this one, if you heat it, what happens? you'll be having calcium oxide, magnesium oxide, and CO2. So you can use calcium carbonate or dolomite, right? If you use dolomite, if you heat it same way, you'll have this one, right? This is also again a reversible reaction. Okay, the reversible reaction. So calcium carbonate dot magnesium carbonate, this is dolomite. If you heat this, you'll have calcium oxide, magnesium oxide, and CO2, right? Then also, then again what we are doing, we are adding calcium oxide to the water, right? So here also same way, if you add this, so calcium oxide present here will react in the same way. Apart from that, so here see you have a calcium oxide here also present, right? So here we are directly adding the calcium oxide form, right? So here also what will be the observation, you'll be having these two are solids, calcium oxide and magnesium oxide will be solid. So at the end of the reaction you'll be having a white powder like this, right? So you can't separate calcium oxide and magnesium oxide, right? By seeing it you can't separate, this is magnesium oxide, this is calcium oxide KLa, you can't separate it, right? So you'll be having one solid you'll be having, right? So it will be mixture of both. So when you add this, the calcium oxide present will be reacting as shown here, right? Previously as shown, it will be reacting and will be forming magnesium hydroxide, right? Calcium oxide will be reacting as shown in the second step and it will be forming magnesium hydroxide. And what about this magnesium oxide here? That is an insoluble solid, right? That will just precipitate along with this magnesium hydroxide, that will also will precipitate, right? If you use dolomite, okay, if you use dolomite, calcium oxide will react like this and it will finally form magnesium hydroxide. As dolomite will convert have a magnesium oxide also, that will also remain finally with magnesium hydroxide, right? So if you use dolomite, this will be a disadvantage, right? Because you'll be having magnesium oxide along with magnesium hydroxide, right? So if you use dolomite, this is the difference that you'll be having, magnesium oxide will be present. So after that the process will be same, right? So after that these magnesium hydroxide will be filtering and you'll be going with the same process, right? So if you use dolomite, these are the changes, right? You'll be having magnesium oxide precipitating along with magnesium hydroxide, right? So that is the magnesium extraction process. So let's read the resource book and we'll finish it off, okay? Right. Extraction of magnesium, page number 6 in my resource book. So if you all are having the new resource book, the page numbers might vary slightly, okay? So extraction of magnesium, Dow process, right? Raw materials essential for extraction of magnesium by Dow process, right? Above the magnesium production, write the raw materials, okay? Write the raw materials, they can directly question, so I'll write the raw materials also. Raw materials is bittern solution. Write the raw materials near the note, write the in the resource book y'all can write, right? Raw materials needed for magnesium extraction. First one, you need bittern solution, right? Bittern solution you need. Then you need calcium carbonate, right? Calcium carbonate, or you can also call it limestone, right? Better write calcium carbonate or dolomite, ya wish, right? And then you need conch HCl. Third raw material is conch HCl, right? So they can ask directly what are the raw materials needed for magnesium extraction. So I'll give it as a note, right? Bittern solution, calcium carbonate or dolomite you can use. And the third raw material you needed is conch HCl, right? Minerals containing magnesium is abundant in the earth crust, right? Minerals containing magnesium, minerals mean magnesium 2 plus, right? Is present in earth crust, right? But extraction of magnesium from seawater is more profitable, right? As I said before, extracting from seawater is more profitable. Other than sodium plus, magnesium 2 plus is the most abundant cation in seawater, right? The number one is sodium plus and number two is magnesium 2 plus, right? Right, in the seawater if you take, second highest is the magnesium 2 plus. In seawater about 0.13% by weight is magnesium. Then highlight magnesium is the Second most, right, they have given magnesium is the most abundant cation in seawater, right? So highlight that and write second most abundant, right? Magnesium is the second most abundant cation in seawater. The sentence must be like that, right? So otherwise, if you highlight magnesium is the most abundant cation in seawater, the meaning might change. So highlight the sentence magnesium is the most abundant cation in seawater and change it slightly to magnesium is the second most. Second, maybe put a second like this, okay? Second kila dala put a like this, you put, right, near the magnesium is the near the after the, put like this and put second, right, and highlight the sentence, okay? Magnesium is the, then you will read this, magnesium is the second most abundant cation in seawater, right? And also highlight from the first paragraph the second line, okay? Extraction of magnesium from seawater is more profitable. Highlight that, I forgot to say that. Extraction of magnesium from seawater is more profitable. Highlight that also, right? So other than sodium plus, magnesium 2 plus is the most abundant cation in seawater. Write second and highlight that also. Magnesium 2 plus is the second most abundant cation in seawater, right? And in seawater, about 0.13% by weight is magnesium, okay? So the solution discarded at the last stage of producing salt from seawater is called bittern. So what is bittern? From the seawater, after removing sodium plus, the remaining solution is known as the bittern, right? So that is the definition they have given for bittern. The solution discarded at the last stage of producing salt. So after removing salt, the solution obtained at the last stage, right, that is known as bittern. So highlight that sentence, okay? Highlight it. The solution discarded at the last stage of producing salt from seawater is called bittern. Highlight it, okay? As bittern contains significant amounts of magnesium ions, it is more suitable to use bittern to extract magnesium, right? Because bittern has mainly magnesium 2 plus, right? Either seawater or disposable brine obtained after the reverse osmosis of seawater is suitable for this. So highlight that, either seawater or disposable brine obtained after reverse osmosis of seawater is suitable for this. Highlight that. So what is that? That is, they are giving the sources to obtain bittern, right? So you can obtain bittern either from the seawater, that is after removing sodium plus, the usual way you can get the bittern, that is the first one, either seawater, or disposable brine obtained after the reverse osmosis of seawater. What is that? No need, right? Just remember the sentence. You can obtain bittern either from the seawater or from disposable brine obtained after reverse osmosis of seawater. Just memorize it and finish it off. No need to understand, there is no point, okay? Right, and then we go to the main steps of this process can be briefly presented as follows, right? Step 1. This is the step 1, right? The main aim of this step is the production of calcium oxide, right? Main aim is the production of calcium oxide, which is obtained by the thermal decomposition of limestone, right? This is the limestone thermal decomposition we obtain. Dolomite also can be used for this process, right? You can use dolomite also, right? So they have given this reaction, calcium carbonate, heated calcium oxide and CO2. Also they have given the dolomite reaction. I have erased it. So they have given the dolomite reaction also. You had to remember both, okay? As this reaction is reversible by designing the thermal decomposition process, carbon dioxide gas is efficiently removed, right? So here this is a reversible reaction, right? So by removing carbon dioxide quickly, this forward reaction is favored. According to Le Chatelier's principle, if you remove carbon dioxide, the concentration of carbon dioxide will decrease. So the system doesn't like it. It will try to increase the carbon dioxide concentration. Therefore, forward reaction will be favored. So by removing CO2, the forward reaction is favored, right? So that is what they are telling in that, okay? So contamination of calcium oxide with calcium carbonate is a disadvantage. Contamination of calcium oxide with calcium carbonate is a disadvantage. Highlight that. I explained it, right? So there is a disadvantage, that is the presence of calcium carbonate along with calcium oxide. That is what they have given here. So highlight that sentence. Contamination of calcium oxide with calcium carbonate is a disadvantage. Right. Now step 2. Step 2. The object of this step is to produce magnesium hydroxide from the solution, that is the object is to produce magnesium hydroxide from the solution containing magnesium 2 plus ion, right? From the solution containing magnesium 2 plus ion. Underline solution containing magnesium 2 plus ions, underline that and put arrow and write Bittern, right? Bittern solution. The solution containing magnesium 2 plus ions, underline it and put arrow and write that Bittern solution, right? They are referring to the Bittern solution, right? The oxide produced in the first step. So if you are using calcium carbonate, the oxide will be calcium oxide. If you are using dolomite, the oxide will be calcium oxide dot magnesium oxide, right? So the oxide produced in the first step are reacted with bittern. So what they are doing, we are basically adding bittern solution, right? So added reacted with bittern solution. Here calcium oxide reacts with water. Calcium oxide reacts with water, forming calcium hydroxide, right? And calcium hydroxide dissolves slightly in water, right? Dissolves slightly in water, giving calcium 2 plus and 2OH minus, right? And OH minus ions. Since the solubility product of magnesium hydroxide is lower than that of calcium hydroxide, magnesium 2 plus in the solution are precipitated as magnesium hydroxide. The reason for the precipitation they have given, right? The reason is, those who haven't studied KSP, no need to worry, right? The reason is KSP of calcium hydroxide. KSP of calcium hydroxide, right, is higher than KSP of magnesium hydroxide. That is the reason why magnesium hydroxide is precipitating, right? That is the reason. So if you all want, right, those who, if you all didn't understand this, no worries, right? They won't ask this much, they can just ask this point, right? What is the reason? Then you can write this. So if you didn't understand, you must have the knowledge on KSP. No need, right? No need. This is enough, right? This is enough. So as they have given in the resource book, I have also given, right? KSP of calcium hydroxide is higher than KSP of magnesium hydroxide. That's the reason for the precipitation of magnesium hydroxide. If you remember that, then okay, it's more than enough, right? With this, more and more calcium hydroxide goes into the solution, releasing OH minus without removing calcium hydroxide as a precipitate. It dissolves. The amount of calcium oxide required to precipitate magnesium 2 plus in the solution is added. Precipitation of calcium hydroxide with magnesium hydroxide is a disadvantage. Highlight that. Precipitation of calcium hydroxide with magnesium hydroxide is a disadvantage. That is this point, right? Because only certain amount of magnesium 2 plus is present. If you are having excess OH minus ions, then here there will be OH minus ions, then calcium hydroxide will be present also, right? So therefore, if you are having, so you must be concerned about adding the calcium oxide, right? So the amount must be concerned, but however, after precipitating, you will be having both calcium hydroxide and magnesium hydroxide, that you can't avoid, right? So that is a disadvantage in the step 2. In the step 1, what is the disadvantage? Precipitation of calcium carbonate along with calcium oxide, right? So that is the step 2 basically. You'll be having the 3 reactions. All these 3 reactions are present, and it's better to write the physical states also. Write it, okay? I think you all can write it. Okay. And step 3, what we are doing is we are filtering the magnesium hydroxide and we are adding conc HCl, right? So magnesium hydroxide formed is filtered and removed and reacted with conc HCl. Highlight conc HCl, okay, to get magnesium chloride, right? So they have given the reaction basically. This reaction is not given in the resource book. If you all want, you all can write it, okay? Otherwise no need, right? It's better if you all can write. This is how the HCl is produced from the chlorine gas, right? Right. If burnt dolomite was used, calcium oxide in it reacts with the magnesium 2 plus. As I explained, the calcium oxide will react with the like this. It will go through these steps. But as MgO is soluble, MgO will be mixed with magnesium hydroxide. Magnesium oxide will be just remaining along with magnesium hydroxide, as I explained earlier, right? If dolomite was used, what will be happen? That is given in the second paragraph of step 3. Right. Step 4, the solution is heated strongly. We are heating the solution to remove the water present in the magnesium chloride, right? So the solution is heated strongly to vaporize water. Okay, then it is dried so that the amount of water crystallization becomes considerably low. Okay, the dried salt contains about 16% water. Okay, what we are doing is we are heating this magnesium chloride, right? So it will be becoming magnesium chloride dot 6H2O, and again further heating 4H2O. Again you further heat it, it will become finally to 2H2O. Then what we'll be doing is we'll be fusing it, we will be melting it, right? So first the solid formed is fused, right? We are fusing it in steel chambers where the electrolysis is done, and then it is electrolyzed. First we'll be fusing it and then we will be electrolyzing it, right? So during heating for fusion, all the water gets completely removed. While heating, the dot 2H2O, that will also be removed, right? So that is what I was saying. The temperature in the cell is maintained within the range of 700 to 800 degrees Celsius. This is the temperature within the cell. Okay, since the melting points of magnesium chloride and magnesium metal are 714 and 650 respectively, the temperature of the fused salt should be maintained above those melting temperatures. Okay, as magnesium metal formed during electrolysis of fused salt exists in mole state, so here the magnesium metal will be in molten state or liquid, right? Its withdrawal from the cell is easier, right? I forgot to mention about it. The density of the molten magnesium at its melting point is 1.5, right? Okay, now here you will be getting magnesium, right? You'll be having magnesium basically, right? So you can cool it. Before cooling it, you had remove it, never. I forgot to mention that. So inside this chamber, so after the electrolysis is finished, you'll be having magnesium liquid, right? Also you'll be having magnesium chloride, right? Some remaining magnesium chloride also will be present in this solution, right? So after the electrolysis is finished, these two will be present, right? So then you will be giving some time to settle. You can give some time, and what you will have is, you will be having, after giving some time, you will be able to see two layers. Right? The top layer will be magnesium liquid, right? And the bottom layer will be magnesium chloride, right? So after electrolysis is finished, you will be having magnesium liquid and magnesium chloride in the solution, because all the magnesium chloride won't undergo the reaction, right? Some amount of magnesium chloride will be remaining. So at the end of electrolysis, you will be having both these compounds, right? Magnesium and the magnesium chloride. And when you leave it for some time, you will be able to see two layers, right? One is magnesium chloride and magnesium liquid. So the magnesium liquid will be on top of the magnesium chloride layer. What is the reason for that? Is the density of magnesium is very less means lesser than magnesium chloride. Density of magnesium is lesser than magnesium chloride, therefore it will float in the chamber, right? So by following some methods, you can remove this magnesium and then you can cool it and you can get the solid magnesium, right? So I forgot to mention about this. And also one more thing to remember, in the industry, for cathode and anode, we are using special metals, right? For the cathode we are using graphite, and the anode we are using graphite, and the cathode we are using steel, right? So mention that also. So in the industry also we are doing this. For the anode we are using the metal graphite, right? We are using graphite for the anode. Graphite is used for anode, and for cathode steel is used, right? For anode graphite is used and for cathode steel is used, right? Okay, so that is what I have told here. As magnesium metal formed during electrolysis of the fused salt exists in liquid state, molten state, its withdrawal from the cell is easier. Okay, the density of molten magnesium at its melting point is 1.58 grams per centimeter cube, while the density of fused salt is 1.68. Thus fused salt, right, fused magnesium floats on fused magnesium chloride, right? So after forming magnesium chloride, at the end of the electrolysis, you will be having both these compounds, right? So when you leave it for some time, you will be able to see two separate layers. The top layer will be magnesium and the bottom layer will be magnesium chloride, right? The reason is the difference in densities. Okay, So anodic reaction I have given, chloride converting to chlorine and to liquid. So highlight, so you have reaction at the anode, right? So anode, highlight anode and graphite, right? Anode and graphite. So industrially for the anode we are using graphite, and for cathode we are using steel, right? So you all might ask, why sir we are using steel and why are we using graphite for anode and steel for cathode? I also don't know. So industrially they are using this. There might be other reasons, okay, that is not needed for us, okay. There may be other reasons which is not needed, okay. Right, and chlorine gas liberated is used to produce HCl, right? The produced chlorine is used to reproduce HCl, right? I have given the reaction also, right? Okay. And HCl is reacted again with magnesium hydroxide. That is the step 3, okay. And reaction at the cathode they have given, highlight cathode and steel. Cathode and steel, inside the bracket they have given steel, right? So cathode steel, and that is they have given this reaction, magnesium 2 plus 2 electron giving magnesium, right? So liquid magnesium formed is taken out from the cell. From this about 99.8% of magnesium can be obtained, right? Purity of the magnesium is 99.8. they can ask in MCQs or essay also they can ask, okay. So as the melting point of magnesium is about, so highlight 99.8%, okay, highlight that also. As the melting point of magnesium is about 650 degrees Celsius, it exists as a liquid at 700 degrees Celsius, okay, right. And finally you have strong and lightweight metals are required for aircrafts and vehicles. For aircrafts and vehicles you need strong and very light metals, okay. So magnesium metal is very important for production of alloys to have this kind of properties. So highlight the full sentence, okay, highlight both the sentences. That is the use of magnesium, okay. And in the production, release of CO2 to the atmosphere is a disadvantage, yeah. So CO2 is added to the atmosphere during the burning of limestone, I said, okay. During the burning of limestone, CO2 is added to the atmosphere, or dolomite also. When you burn you will be having CO2, right? And also combustion of petroleum products to obtain higher temperatures. To obtain this higher temperature we combust petroleum products. So while combusting, CO2 will be released, right? So by these two ways CO2 is released to the atmosphere. So you have to remember the two ways by which CO2 is released to the atmosphere, right? First is by the combustion of decomposition of by the burning of calcium carbonate you will be releasing CO2, and also by the combustion of petroleum products to reach high temperatures you will be releasing CO2 to the atmosphere. So highlight that also. So there are two methods to release CO2 to the atmosphere. Highlight the both the methods, okay, so they can ask that. So that's it, magnesium extraction done. So they have given the structure, right? Graphite anode, Cl2 gas. Just look at the words, okay. They might just give you in the question to scare you, to scare or bayakara then, so they can give to scare, but nothing is there, okay. You can see fused magnesium chloride. So I have drawn in simple terms, okay. Steel container. So you all can look just at the diagram, just read it once, that's it, okay. So that's it, magnesium done. So next class we'll be doing caustic soda production, okay. So I hope you understood the section magnesium extraction. So out of 9 industries, 1 industry is done, okay. So if you are having any doubts, if you all are having my number, you all can WhatsApp, or I might upload to the YouTube also, might be, okay. So I might upload to the YouTube, so you can ask me in the comments also if you want, right. Right, if you all wanted to join our classes, WhatsApp me to this number 0777 493632, right. So WhatsApp to this number, so I'll give you the information regarding the classes, okay. So that's it guys, have a nice day, and we'll meet with the next industry, right. Within few days I'll try to upload, okay. Okay then, don't accumulate, don't keep recordings, okay, because you all are having only 3 months left. So try to finish it off, okay. So because industry is a very important lesson, right. So I said you in the starting of the class also, you will be having 12.5 marks, right. Approximately 12.13 marks will be having out of 100 for industrial chemistry. So those who are aiming for a industrial chemistry is very important, right. Don't neglect it, okay. Right, okay then, have a nice day, see you guys, bye.